So, so actually there was a really interesting quote yesterday from Zoe. So, code is not just syntactic. You need to understand deep, complex architectures, dependencies, and code bases. Now, who here has worked on a code base that you didn't write? Basically everybody. Who here has worked on a code base that you didn't write, that the author has left, and you've got an undocumented function that you have no idea what it does? Wow, look at that, 100%, I think. The challenge with code bases is they are living documents. They are not only, it's not a doctoral thesis. It's not something you write and then never open again. For anybody who's completed a doctorate, you know exactly what I mean. I have my thesis on its shelf, and it hasn't been opened in 10 years. But code is said is a living document. The problem is, as it evolves, it tends to get a bit mucky. Things get left behind intentionally, unintentionally, random bits of commented out code, random bits of non-commented out code. So the whole point of ScalaClean was saying, well, actually, if I look at the program as a whole, can we work out dead bits? Can I work out which piece of these code? Because when I'm in IntelliJ, or metals, and I go to a method and I go find usages and there's nothing, I know that is dead, and I can do it at a local level. But there is no way in those tools to do it at a global level, to say, within this entire application, within this code base, what's dead? And the interesting thing is there is techniques for this. Static code analysis, whole program analysis, allows you to make determinations about code. And if I had to put money on it, I would say if you pick a large enough code base, any legacy code base more than 5 years old, I would say 20% of the code is dead. If I didn't have to put money on it, I would estimate it's close to 30%. So let's deal with one important thing. Let's deal with the current state of the project. When I first started talking about it, it was vaporware. It was just a nice idea. It's like, oh, this is the dangerous statement. This is really easy, right? We've got SemanticDB. We've got ScalaFix. We can implement this in a weekend. But it's not vaporware anymore. Instead, we reached the next stage where it was completely broken. I had a unit test which passed occasionally, and for any code base of any size or any code base at all, it basically broke in historic ways. We've improved. This clicker's not working very well. So now it is probably broken. So you can now, the fun part is, you can now run this on your projects. But, as is always the case with any open source project or any tool at all, beware. Because, does anybody recognize this? Monty Python? So it's 50 years of Monty Python today. So I thought I had to add it. ScalaClean, when it goes wrong, it tends to be a little overly aggressive because it goes, I can't find this, it must be dead, I will remove it for you. Which means if you're not careful, it will remove your entire base. So please, please, if you take nothing else away from this talk and you do try and run it, please commit your code first. I will not take any responsibility if you manage to delete your entire code base. So as I said, it is runnable. You can actually check it out. There aren't published artifacts yet, but there should be soon. But it will probably break your code in horrible ways. It'll probably delete more than it should, and that's something that's part of the interesting part of this project, is the fact that if I miss a reference, that I assume things are dead that aren't dead. So it's got to be very correct to actually work well. But it has testing. It's sort of working, and we're improving it, and we're now in that bug fix phase. We've got the mechanics in place, we've got the test framework in place, and now it's really a question of finding the edge cases and building it out. But why do we care? I need to sort of step back a step and talk about software quality. The challenge is we are maintaining, as I said at the start, living documents. The code changes, the team changes. What your code is actually doing changes. And as you write code, you write a method, and then an hour later you refactor the code, but you don't necessarily clean up all the missing methods. And especially on a large codebase, I've worked on a codebase which is so large that the change rate is so high that I could never keep up. I could never, even in a day, I couldn't review the code. It's like watching all the videos on YouTube. Right? The number of hours of videos that end up on YouTube in a day is more than you can watch in a lifetime. And the problem is debt continually accrues. Right? It's one of those things that if you write code, bits are going to change. We're going to continue to get sort of small bits of technical debt. But the other challenge is measuring it is really hard. Unless I'm in a class and I see a method and I go, oh, this method is dead, you don't even see some of that debt. So working out what to delete, how to maintain that code, how to keep it clean is hard. But it slows you down. We were talking about this yesterday. When Zainab was saying the 3 ways of speeding up your compile, right, is you do less work, you do the same work faster, or you do the work in parallel. Right? And that's true of any optimization problem. But those pieces of code don't just slow down your compile. When you do refactoring, you've got to fix up things. And I spent days fixing up things and trying to make it all work and trying to make it all compile to get to the end and realize the thing I've spent 48 hours of my life trying to fix is actually unused entirely, and I could have just deleted it at the start. So, is software quality important? And the answer for me and Martin Fowler is yes. You need to keep track of that debt. It's like interest-only repayments on a mortgage. Right? If you do nothing on an interest-only repayment mortgage, at the end, in 25 years, you still don't own a house. Right? You're just paying the interest to effectively borrow the house from the bank. But as technical debt accrues, you're paying more and more interest. And in fact, I've seen large projects where what happens is the technical debt gets so high that some new manager comes in and decides the solution to the problems and the support issues and the life cycle of this project is to scrap it and build a new one. And generally, especially in larger organizations, it's the classic legacy code problem. If you have 12 legacy systems and you write a new one to replace 12 legacy systems, what you end up with is not one system, you end up with 13 legacy systems. Right? So how do we keep clean code? Well, we try hard, right? We pay attention to this stuff. We try not to reinvent the wheel. My biggest advice, if you ignore everything else here, is if there is a good library out there, go and use it. Don't rewrite logging. Everybody's done it. Everybody's written a simple logging thing with a print line and a thing. And then at some point, you're going to have to go back and fix it and put in a proper logging framework, because suddenly you now need different levels and you need different stuff. It's better to use the frameworks that exist and pay a little bit of the upfront cost a little earlier. And conscientious design. We think about how we design software, we think about the structure, and we keep the house clean. But I know what you're thinking. These tools already exist. Right? There is loads of tools to do code analysis. Has anybody here, who here has used one of these tools? 2? 3? 4? Okay, so we've all run these tools, and I guarantee if you run these tools, they will find something interesting in your code. Right? So what's the problem? The problem is they're local information. These tools run at the level of a source file. So IntelliJ can correctly point out that the private method is unused within a scope. But it doesn't say this public method is unused or within your entire code base. And there's a bunch of questions it can't answer. In fact, one of the challenges with languages that run on the JVM is the target we generate, the class file, is forward references only. Right? I know I can look at the code and say this calls foo, but I can't look at foo and say who calls it. Or I can't do it. I can do it on a case-by-case basis, but I can't do it globally. And who extends it? Who uses these tools? So, it's great for determining, guaranteed null pointers, invalid code, dead code paths, but they're not good at recognizing bigger patterns. And to do that, you need to now capture the graph. You need to go and look at the forward links, traverse them, work them out, and then apply that knowledge to your program. And in fact, when you open IntelliJ, and it spends a time, when you open a new project and it spends a bit of time grinding away, this is exactly what it's doing. It's creating a bunch of indexes so it knows more information about your code. It's generated information and knowledge by looking forward to allow you to look backwards. And the fun part is it is a graph problem. Once you see it as a graph problem, suddenly it becomes a lot easier. So first off, we generate the full graph. We explore the program. We look forwards. We take every reference. We see every entity. So I say, here's a class, here's a trait, here's an object, here's a method. And I look forward. I say, what do I know about this method? I know this method calls that method. I know this method belongs within this class. And in fact, the information you need is actually really comparatively small. But once I have those links, then I can form a graph. And we can use graph techniques to infer interesting information. And then we can apply that to doing fun parts with the code. But the point is, you need to traverse this thing. You can't infer it from the class files without doing it for every class file and then resolving. But one of the problems with graphs is this is the build graph for Akka, not the class graph. It's the build graph. So even just the project itself is complicated. And the real problem is, I can't remember what this is now. But the graphs get really huge really quickly. Right? They get to the point where you can't reason about them. But we can use graph techniques to address this problem. So what's the plan? Capture the dependency information. Now this was a step that I thought was trivial. I thought this would take me an afternoon. And then use that information to do interesting things. What can I determine about your program? And I've got a few ideas and a few thoughts about all the stuff we can do a bit later on. But what do I need to assume? Well, actually, the previous speaker, Francois, talked about the ahead-of-time compilation in Graal. And one of the things he said is you have to, at some point, deal with a closed world assumption. You have this problem, which is, in the JVM, theoretically, for any arbitrary class, I can actually redefine quite a lot by loading a different class path. What's alive depends on what's being used and what's being run. So when we talk about a library, is a library method alive or dead? Well, it depends who's using it. But because of this, we've sort of ignored this whole idea. But the truth is, most of you are writing applications. Right? Within your organizations, you are writing code that actually runs, right? Be it a Play application, be it a server, all of those things do have a closed world assumption. At the end of the day, you're running it with a class path for a given task. And at that point, ignoring reflection for a bit, and we'll come back to that, you now have something you can analyze. You can say, for this project, for this code base, what's alive and dead? So to do that, we need to mark all of the entry points. Now, some of them are really easy. A main method on an object, that's trivial. But we can also add annotations. We can actually add rules, we can add logic. So you can say in a play application, all of the public API points are used. Or I can add annotations to the code. Or I can use regexes. I can have a list of classes, which I say, these are the public interfaces to my things. So if I'm a library author, I should be able to say, this is the public interface. What I want to know is dead code that the public interface doesn't get to. So let's have a look at how we actually do this. Capturing the information. Now, where I started was, the reason this project sort of exists at all is I went, hang on a minute, SemanticDB basically has all this information. Right? I can take that information and turn it into a graph. That turned out to be mostly true. And the problem for dead code analysis, for example, is mostly true really isn't good enough because it marks stuff as dead that isn't dead. And that's the worst possible case. I delete code from your project that you care about. So I've also fiddled with compiler plugins. And for certain cases where you've got jar files, you actually need to go and do reflective stuff. So that's one of the challenges. And it's actually the biggest challenge of the whole thing is actually working out that data. Actually applying it turns out to be really easy. So I'm going to have to go fairly fast through this, but I want to cover why I think we can do this and what the useful stuff is. So my favorite one, and the one I've been focusing on, is dead code removal. As I say, in any large code base, I think a significant portion of that code is dead. And if I remove 20% of the code from your code base, that makes the code compile 20% faster. Privacy scoping. So making things as private as they're allowed to be whilst allowing your program to function. Why do we care about that? Because things like outline typing, which allows us to do parallel compilation, and lots of useful things, and actually just completions in your IDE are really helped by the fact that your private internal methods are private. Something Zainab talked about yesterday, build profile analysis. If I've got a build graph, by moving code around that doesn't depend on something else, I can potentially speed up your build significantly. And I think there's a bunch of other stuff which I haven't even thought of, and I get lots of ideas at conferences about people talking about this. So, dead code analysis. So doing it by hand is really hard because of things like circular references. So when I go and right-click, say, find usages, if I have a build site, if I have a cycle of references, it's very hard to prove to myself that the code is dead. And very long chains, and it can be really painful to do it by hand. It's easier in pure functional code. If this method is not called, if this function is not called, it's dead. So I'm going to wander through this because I want to get further on in the talk. So how do we do it? What we do is we mark it and we use graph coloring. So by traversing the graph, if this method is used, implicitly its class is used. If the class is used, its package is used. And I can traverse up just by traversing through from the main entry points, recursively visiting the graph and coloring it. And when I end at the end, anything that's uncolored is dead. So one interesting point is actually the comparison between what is dead within the code, the main code, and what's dead from the test code. So I might have a method that's used in test code, but is completely dead otherwise. Right? That's probably worth removing. So coloring, as I said, is just walking through and marking things and then removing it. Limitations, it can be difficult to detect the entry points. You need to annotate APIs in some way, and we can use annotation. Privatisation, so reducing the scope. So reducing visibility helps developers with completions and all sorts of other stuff. And it's good practice. And it helps with incremental compilation. One of the things, you want to do incremental computation is, has the interface of this thing changed? Because if the interface hasn't changed, I don't need to compile the downstreams. Right? I can just compile that module, and as long as the API hasn't changed shape, I can leave the downstream code as is. I might need to run the test, but I don't need to recompile all the code. And this really helps with pipeline compilation. If I can limit the interface, then I only need to compile those public interfaces, and I only need to put types on those public interfaces. So by using ScalaFix, I can say, I'm going to minimize my public interface, and then I'm going to add types to all those public interfaces. So, as I said, hiding stuff from IntelliJ is great. So yeah, this is all this stuff is lots of fun. I will, obviously there will be time for questions at the end, and I will make sure we talk about that. So, but this is the thing, this is, when we talk about builds, a lot of people care about build performance at the moment. So with pipelining, once I've done type checking, I can start compiling the downstream modules. Traditionally, you would have, module 1 would be completed to code gen before I start compiling module 2. Right? But the fact is, nothing in module 2 at the point of compilation cares about what's actually in the bytecode. What it cares about is what types and interface are available. Outline typing goes one step further. What we do is we break typing into 2 fragments. The first one says, type the things that people are going to care about. Type the public interfaces. And then I'll worry about making sure all the methods actually implement the right type. But first off, just type the interfaces, because that's all the information the downstreams need. And you can really, so we can start to overlap them more aggressively. And the fun part is, there's even a step further, which has been discussed, which is, once I've got the public interfaces, between files within the same compilation unit, they're now independent. So if I do outline typing first, in theory, I can parallelly compile within a module, which is sort of partially what Hydra does. I don't know all the details of the Hydra's internal, but this is the kind of tricks you can pull. I talked about build diamonds. So often in very large projects, you end up with this kind of build structure, where there's a couple of core modules at the bottom. They fan out to a bunch of sort of mid-layer stuff. Then they often fan in again. You often end up with a build pipeline that depends on one critical module in the middle. Now I know which code calls which code, and I know which module the code's in. I can actually suggest that this class moves up or down. If nobody cares about it, I can move it up. I can move it later in the build chain. If it's a critical build component, I can move it down. I can move it so it's done earlier, or I can move it so it's in this case, the central module can be broken into 2 modules that frees up more parallelism. And there's more. One of the fun parts, there's a bunch of things I keep coming up. I keep adding to this list whenever I come to a conference, because I keep speaking to people and they come up with new ideas. So unused parameters. Actually going through an entire hierarchy and going, well, actually, the second parameter of this interface is unused. Let's just take it out. And I can do that automatically. There's nothing, it's mechanical. Once I know it's dead, it's a mechanical operation to fix. Remove constant parameters. There may be cases, and this becomes more interesting because it's like, actually, I probably want to review this before I do it, right? I don't just want the code to go and minimize and remove all the constants. If you think about what the JIT does from the previous talk, it will go and do lots of clever things. It'll remove code that becomes irrelevant. But I might not want to do that automatically because that constant might be there for a good reason, and it might be constant now, but it might not be constant in the future. And you can do things like relaxing types. In fact, Diego, who's not here this time, unfortunately, came up before this project even worked and put an idea in the bug tracker about relaxing types. So if B can replace with supertype A, then move it to A. And the idea is you're coding to the interface, not the implementation. And this just makes your code more general and I think better. So what are my observations about this? This is a really interesting project, and I've had a lot of fun doing it, and I'm sure I'll continue doing so. Tooling is fiddly, and I'm sure the metals people will tell you this, and the SBT people will tell you this. There's a lot of random edge cases. There's a lot of silly stuff, like the fact that an SBT build doesn't have one source root, it has a whole bunch of them. But the compiler doesn't know that. But you need that for SemanticDB, and lots of silly fun stuff, which is, as I say, where I thought the challenge for this project would be was in the analysis. I thought that getting the data would be easy, doing graph walking and doing interesting things would be really hard, but that would be fun. And it turns out the problem is getting the data, not doing the graph walking. And we're implementing complex language. One of the biggest challenges for me is there's no canonical representation of symbols. There's a real mix. The best canonical representation we have is a SemanticDB symbol. But it varies. Inside the compiler, there's no canonical representation. That turned out to be quite a challenge. And reverse engineering stuff is hard. What's next? We're going to continue doing it, fix all the bugs. That's the plan. Please come and help. It'll be a lot of fun. Testing on bigger projects, I have a Pocket code base of over 5 million lines of code I want to run this on. And seeing where the data leads us, I think there's a whole bunch of interesting places this opens up. So that's it. So whole program static analysis is fun. I think it's an interesting area to play with. We don't yet have a turnkey solution, but it is now runnable. Come and have a play. And there's lots of work to do. So that's it. Thank you very much. I'm out of time. So questions?
Yeah, thank you very much. So about the questions, someone's asking, what if I'm writing a library or a framework? A lot of methods are not called apart from the tests because they'll be invoked by code that depends on my library.
Yes. So this, I think I did cover this at one point, which is what you're going to need to do as a library author is annotate your public interface. Whether that's at the class level, whether you can say, with a regex, you can say this class is alive and anything it refers to is alive, or putting annotations in the code. I'm really open to discussion about the best way of representing this for library authors. So please do come and grab me afterwards to discuss, because I have a bunch of ideas and I don't know the best way of doing it.
Yeah, thank you. So the second question is, when do you estimate will the ScalaClean be production ready?
I'm hoping that it'll be, so it is now runnable. I'm hoping that over the next month or so, it'll get to the point where the majority of cases will work out of the box. And then it's, I think that the challenge for this, like all tooling, is it's then hunting the edge cases. But what I'm hoping as I say, within the next month, it'll be in a situation where you can run it on your project, and if it doesn't work, you can submit a bug report, and we'll work out which reference I'm missing or what's broken, and then add to it. It should be. The idea is the tooling's there to make that cycle very rapid. Once we find a bug, it should be very easy to kill it.
Okay. So the next question is, how do you deal with reflection?
I don't. It's easy. No, but this is the same as the API problem. How do I mark things as alive when they're called reflectively? And my answer is annotations, regexes, and some rule-based marking. For example, for play, you might mark it based on the fact that it's called in the HTTP API.
Okay, so what about code instrumentation to get actual usages?
So getting actual usages from a runtime app, so running it and saying, well, actually, this is a really interesting question because it's a third axis. So you've got this code is reachable. This code is reachable from tests, and this code is reachable from production. And the third axis is this code might be reachable, but it's never used. So I think you can overlay that data, and I think there's multiple data sets. And one of the things I've been talking to a couple of the guys with is, how do we visualize this data? I think there's a whole data set here to be looked at that we haven't got it yet, and once we have got it, what can we do with it? And how can we overlay more data?
Okay, so the next one is, you mentioned that graph build on top of the SemanticDB was only mostly correct. What was the missing incorrect information in SemanticDB?
So one of the pieces of information I was missing was inheritance hierarchies. Specifically around when you have a method foo, I need to know to correctly work out the dependencies, I need to know all of the interfaces that it implements and all of the things it overrides. And I need to be very specific. So when there's multiple foos, I need to know that I'm overriding that one, not I'm overriding foo. And I found there were some information gaps there. And what I'm hoping to do is work with the SemanticDB guys to actually add that information back, because I think it's useful information outside of this. I think it's useful for metals and things as well. And I think that some of that work has been done. There's as seen from, which is one of the methods that you need to do, is actually now implemented in metals.
Okay. Yeah, we have another question. To make ScalaClean production ready, how can I help you?
Come play with the project. So the fundamental thing is we are basically at a point where we have a runnable tool. The problem is what you'll find is when you run it on your project, it'll probably declare some stuff dead that isn't, and we need then to work sort of backwards and work out what missing reference, what missing forward reference I'm missing, so it gets marked. So come and join the project. I haven't got a Gitter room, but I will have a Gitter room very shortly. I will tweet about it, and I'm sure ScalaSphere will retweet. So come and join and play. I think it's a really fun thing to play with.
Okay. And the last question is, would you be able to go backwards to find potential entry points?
Backwards to find potential entry points. You can find the critical points. You can find the points that keep an area alive, which is, I think, sort of what you're saying, whoever's asked the question. So I can find sort of this method here keeps alive this entire sub-project. So you can sort of work out that kind of entry point. I'm happy to discuss that one offline because I'm not quite sure what information you're trying to gather.
Okay, so I think this was the last question. Thank you very much. Ladies and gentlemen, please give another round of applause for Rory.
Thank you.